Now, based on Hubble's law, the Big Bang occurred about 13 to 15 billion years ago. Again, you should think of this as an explosion of matter and space, not matter into space. This is not an explosion like a firecracker that blows up and sends pieces off in all these different directions. It's that the space itself is exploding and dragging everything with it, and things are coming apart because space is pulling it apart. Now, to understand what happened, we take the laws of physics as we know them and apply them to a very hot, dense matter that must have existed when everything was pressed together. Now, if we apply the laws of physics, we can deduce a history of the universe. And we can go back to very, very early times. And it's a logarithmic scale, so we're looking, maybe at 10 to the minus 33, 10 to the minus 35 seconds. That's a really short amount of time. That's about where we're at. We don't understand what happens all the way to 0, but we're getting close. So at 1 microsecond after the Big Bang, the temperature is about 10 to the 13 K. That's hot enough for photons to create quarks and antiquarks. Now, a quark is a subatomic particle. A proton, for example, if you break it apart, will break into 3 different quarks, 1 up quark and 2 down quarks. So we can start creating the quarks, the things that the subatomic particles are made out of. And at this time, at 1 microsecond, the diameter of the universe is smaller than the Earth's orbit around the Sun. The universe at this point is expanding at nearly the speed of light, and as it's doing that, it's cooling rapidly. The lower temperature no longer produces quarks and antiquarks. Now, those who study subatomic physics show that that dictates that existing quarks and antiquarks annihilate, but they annihilate asymmetrically, and that leaves an excess of quarks. The surviving quarks then combine to form protons and neutrons. At 5 seconds or so after the Big Bang, the universe actually cools enough that all matter that could be created is created. There's not enough energy left as it cools down for matter to continue to be created. Now, at 3 minutes after the Big Bang, the temperature is a few 100 million degrees. And at this point, about a quarter of all the protons fuse into helium in that same proton-proton chain we talk about this going on in stars. For the next 500,000 years, we get further cooling and expansion. Electrons begin to bind to protons to make hydrogen molecules. And this is referred to as the recombination era. At the end of this period, photons and matter go their separate ways. Photons can't move through a plasma when protons and electrons are all separate from each other. But as soon as they combine and we get neutral atoms forming, then light and matter can go their separate ways. Now, if we consider the ages of several galaxies, we know that galaxy formation had to start very soon after the recombination era. So protogalaxies formed from the gravitational collapse of gas clouds, these gas clouds of the hydrogen and helium that formed earlier. Gravity is too small a force to create galaxies in the time scales that are needed. So there is a need for dark matter to speed things up. Dark matter forms clumps around which protogalaxies form. Areas rich in dark matter clumps form large-scale galaxy chains and sheets. Areas deplete of dark matter form voids. How this all works is still considered an unsolved problem that people are trying to figure out. So as we look at the timeline for the universe, the temperature started off very hot and cools down to about the 3K that we are today. We had at 10 to the minus 33 seconds, we have an inflationary period, and we talk through all these. This is a logarithmic scale, and here we are now, about 10 to the 10th years. Now eventually, the fuel's going to run out. We get dark stars and dark galaxies, if expansion happens forever. But whether it's going to happen forever is still a question to be solved. Now, what was the state of the universe before 1 microsecond? Well, it was even hotter and denser than what we talked about. Actually, the universe is smaller than the size of a proton. And at that scale, gravity is no longer a force of attraction, but one of repulsion. The repulsive force creates this violent explosion, which cosmologists call inflation. That inflationary period happened in a very short time scale. We can't really even imagine how short of a time scale it is. It began at 10 to the minus 35 seconds and lasted until 10 to the minus 32 seconds. Inflationary period ends where the previous Big Bang theories begin. The inflationary models of the universe mark the frontier of our understanding of the cosmos and give tentative answers to several unsolved mysteries. Some models suggest creation from nothing. Others suggest existence of other separate universes. Still others posit that the universe has 10 or 11 dimensions that we only perceive 3 and time would be 4. This is string theory you may have heard of. Finally, these models also try to explain why space is so flat and how all the forces of nature relate to one another. Before the start of the inflationary period, 3 of the 4 fundamental forces, the electromagnetic, the strong and weak nuclear forces, are joined together in a matter described by grand unified theories, GUTS. As the universe inflated, symmetry breaking separated their forces that releases energy. And this energy was then used by the false vacuum, a non-zero energy state with negative pressure. And according to general relativity, a negative pressure manifests itself as a repulsive gravitational force, lasting only for the brief inflation period. So, at this point I want you to stop and I want you to watch the Nightline Big Bang Theory video. This explains a little bit about, it was about 20 years ago or so, the discovery of the fluctuations in the cosmic microwave background, which really is one of the crowning achievements of the Big Bang Theory.